Boker Tov and good morning everyone. Today we start with the actual material of the course, the actual inner product spaces. And what we'll try to do today and in the next few lectures is start from the standard geometry, the standard Euclidean geometry, and little by little try to generalize it to other places, but in such a way that we can retain all the intuition or most of the intuition and most of the result, and we can still apply them in those other places. It might have different names, but still the same. Okay, so let's start. Our starting point is one of the most basic and well-known results in geometry. If we start with a right-angled triangle and name its sides by x, y, and z, and then put squares near the x and y, then the sum of the area of these squares equals the area of the square near z, or in other words, x squared plus y squared equals z squared. Right? This is the standard Pythagorean theorem. So this is our starting point, and we want to take this Pythagorean theorem and ask, can we apply it in other places? Now we can talk about triangles in general vector spaces, right? If you take x and y to be actual vectors, then z is going to be x plus y as a vector. The problem is, of course, the angles. We want to talk about angles in a general vector space. And the question is, how do we do it? So let's start with any angle. We start with this theta, and we want to understand it. So the question is, what is theta? And in general, saying what is theta is really difficult. So instead of talking about theta, I want to talk about the cosine of this angle. Now, if you think about it, the cosine of theta should be a little bit easier to compute, because if you are in the right angle triangle like the one on the left, then the cosine of theta is just x divided by z. However, this whole process is in order to understand what are angles, and in order to understand what is a 90 degrees angle, so we can't use it to actually define cosine of theta. So we need to find something else. And luckily for us, there is a way to write cosine of theta in a simple way. So we should think about this angle as inside the two-dimensional plane. And if we name the vectors by v and w, then cosine of theta is actually this weird expression. Right? It is vx times wx plus vy times wy, everything divided by the square root of the sum of squares of the vx and vy and the sum of squares of the wx and wy. Right, so we have this weird expression, which by no means is trivial. Right? If you didn't know about it, what reason do we have to believe that you can write cosine with this type of expression? Right? This is quite simple if you think about it. You need addition, you need multiplication, you need division, and all of these are the standard arithmetic operations. And the only thing you need extra is the square root, a little bit of calculus. And if you have this very simple operation, suddenly you can define the cosine of theta. And more than that, if you know how to define the cosine of theta, then suddenly you know that cosine of theta is 0 even only if the angle is 90 degrees. So we can define this 90 degrees just by knowing this cosine of theta. So we really have this very interesting expression, and now we want to understand it. By the way, if you want to prove it, you can. Usually the proof goes through the law of cosines, and the law of cosines usually use the Pythagorean theorem. But here we don't want it. We don't want to actually prove it. We want to understand it in a way that we can generalize it to other places. Okay, so the way that we do it is as follows. If you look at the numerator, so this is just vx times wx plus vy times wy, then we use it as a new notation and we write it as the product of v and w using these triangular brackets. Or if you want it in a simple compact way, so the multiplication of v and w with these triangular brackets. So there is a good chance you are already familiar with this type of expression. This is called the scalar product, or in many places this is called the dot product and is denoted by v dot w. However, I don't really like this notation and I will not use it. The reason is that while the scalar product is similar to general product, right, multiplication of numbers, this is not exactly the same. And in particular, this is not associative. So the dot product looks associative. We usually think about it as associative. However, I will only use the scalar product because these brackets are actually important. Okay, so our numerator is a scalar product, which is a very simple expression. Again, all we need to do is to multiply the coordinates and then sum them over. And more importantly, if we take the product of a vector by itself, this is just the sum of squares. Right? So this is what happens in the denominator. So we usually denote it as the absolute value of v squared. So again, a very simple expression gives us both the numerator and the denominator, and you should actually think about them as the angles and the lengths. Right, so the absolute value of v squared is of course what we think about the length of a vector squared. And while the scalar product is not exactly the angle, philosophically it's very similar, right? It is almost the cosine of the angle. And now that we have these expressions, both for the numerator and denominator, we can write the cosine of theta as v times w divided by the size of v and the size of w, right? We normalize by the size of v and the size of w. So again, these weird expressions, once you define this new scalar product, becomes much simpler, much more compact. Okay, and finally, saying that the angle is 90 degrees, meaning the cosine of theta is 0, means that the numerator should be 0, or in other words, v times w should be 0. Okay, so if you want to say that two vectors are perpendicular, we have 90 degrees between them, it only means that the product of v and w is 0. So again, what did we do? We started with the standard Euclidean geometry and tried to find out a very simple way to write it in a formal way. And we found this nice expression, this scalar product, and we can use it to more or less define or more or less think about these three properties, about angles, about lengths, and about vectors which are perpendicular. Great. So this is true in the two-dimensional case, and the question is, can we do it in other places as well? So of course, the first step is to go high dimension, and we can define the scalar product in higher dimension, just the product of vi and wi we sum from 1 to n. And similarly, the length is going to be the sum of squares. And suddenly we have the scalar products in high dimensional vector spaces. And I'm not sure about you, I can imagine vectors in 2 dimensions, I can imagine vectors in 3 dimensions, and I can imagine their angles and lengths and whether they are not perpendicular to one another. I cannot do it in 4 dimensions and above. But suddenly we have this very simple function, and just saying that they are perpendicular in 10 dimensions, in 100 dimensions, is just the product of them is 0. So already we have a nice intuition that we can take higher dimensions that we cannot really see. However, can we take it even further? Right, so this is the question. Because if it was just scalar product, then fine, it's nice but not enough. But can we take it further? And here, very smart mathematicians have thought about this problem. And I think the first one was Giuseppe Peano in the 1900s. And they asked themselves the following question. What are the most interesting properties that a scalar product has that using these properties, we have all the results in the standard Euclidean geometry? Because if you understand these properties, and if you can apply them in other places, if they are true in other places, then suddenly the intuition from the standard geometry can be applied in these other spaces. Okay, so this question, this idea, has led to the definition of inner product. So let's see. Okay, so now we want to define the inner product. So for that, we need to start with a vector space over the real numbers. And the inner product is going to be a function which takes two vectors and returns a scalar. Now, in general, when we talk about multiplication of numbers, it takes two numbers and returns a number. So it returns the same kind of element. But you need to remember an inner product takes two vectors and returns a scalar. Now, this function should satisfy three conditions: the non-negative, symmetric, and linear. So the first condition, the non-negative, for every vector, if you multiply the vector by itself, it should be non-negative. Now the intuition that you should have about this property, the geometric intuition, that its product of a vector by itself is going to end up like the length of the vector, so it should be non-negative. Right? This is the reason that we define this property. Moreover, we want that if the product of v by itself is 0, this is true if and only if the vector itself is 0. So again, the geometric intuition should be a vector is 0 if and only if its length is 0. Right, so this is definitely true in the standard Euclidean geometry, and this is a very important property that we want to have, so we add it as a condition for the inner product. The second condition is that symmetric, so if we take two vectors and we talk about the multiplication of v in w and w in v, this should be the same. And again, the geometric interpretation that the angle between v and w and the angle between w and v should be the same. Finally, we want linearity. So if we fix this linearity in the first variable, it means that if we fix the second variable, if we fix w, then as a function of the first variable, the inner product is linear. Now, this should not be too surprising because this is basically what we expect from a product. This is just a distributive property of standard product. So this is true also here. Now, the linearity by itself, I don't know a direct geometric interpretation, but we will see soon that linearity leads to something which has a very, very interesting geometric interpretation. Okay, so now we have a definition. We somehow generalize the scalar product, and we have to show that there are examples, because if there are no examples, then there is no reason for this definition. So let's move to examples. Okay, so the first example is the standard inner product on Rn. This is the scalar product. And we just take the product of vi, wi, and we sum everything up. So let's just see that this is actually an inner product, and it should be because this is our prototype. This is why we defined inner product. So first of all, this is a well-defined function. If we multiply a vector by itself, this is just the sum of vi squared, which is always non-negative. And if sum of squares is 0, then each one of the squares must be 0. So each coordinate is 0, meaning the vector by itself is 0. Right? So this is a non-negative function. Second, it is symmetric because the standard multiplication of scalars is symmetric. Right? Vi wi and wi vi is the same. Right? So the multiplication is symmetric, so our inner product is symmetric. And finally, this is a linear in the first variable because the product of vi and wi is linear in the first variable. Right? This is the distributiveness condition. So again, all the four conditions hold, and they should hold because we started with the scalar product and we try to generalize it, and this is an inner product. Finally, as a notation, if we think about v and w as column vectors, then we can write it as w transpose times v. And now the dot in the middle is the standard matrix multiplication. Okay, so it's not the dot product, this is matrix multiplication. Now you can also write it as v transpose times w. Both of them are the same. However, I prefer the w transpose times v, and we will see later why this is a little bit better. Okay, the second example is similar to the standard inner product. It is the weighted inner product. It is defined almost the same. We only add weights which are positive di. So the definition is the sum from 1 to n of di times vi times wi. And the way you should think about these weighted inner products, so for example, let's say that we move on the plane and we can move either forward or backwards or right and left. And for whatever reason, forward and backwards are more important to you. So you add a different weight for this forward or backward, right? Because maybe add a larger weight to this direction. So this is what you should think about weighted inner product. And again, you should check that this is actually a well-defined function. It is not negative, symmetric, and linear. Okay, the third example is the standard inner products on matrices of size n times m. So now we have two matrices and we want to multiply them. And the question is, how do we do it? So let me start with the standard multiplication. So in general, you can't just multiply two matrices because they need to match with their sizes. The number of columns in A should be the numbers of rows in B. And if n is different than m, then this is not true. However, we can fix it by looking at B transpose. Right? And now we can multiply A by B transpose. This is well-defined square matrix. Now, if A and B were actually vectors, then this is just a standard inner product and we're fine. If not, as then A times B transpose is a square matrix which is not 1 by 1, so we somehow need to extract some scalar from it, and it should be symmetric in A and B. Right? This is one of the conditions of the inner product. So the way that I see it is, if I look at the diagonal, right, just visually it is the symmetric part between A and B. So it is still not a scalar, so we look at the diagonal and just sum everything up. Or in other words, I'm going to define the inner product between, or the product between A and B, to be the trace of A times B transpose. Okay, so this is a well-defined function. This is just what we proved. And we want to show that this is linear, symmetric, and non-negative. So let's start with linearity. The fact that you are linear in the A, in the first variable, this is because A times B transpose, the matrix multiplication, is linear in the first variable. Again, this is the distributive condition. And trace is a linear function. So composition of linear function is linear. So we know that this product is linear in the first variable. For the symmetricness, we just need to show that trace of A times B transpose is the same as trace of B times A transpose. But A times B transpose and B times A transpose are the same matrix up to transpose. And we know that the trace of a matrix and the trace of its transpose is the same. So both linearity and the fact that it is symmetric is very easy to show. By the way, these are also equal to the trace of A transpose times B and the trace of B transpose times A. And this is because the trace doesn't really care about the order of the multiplication. Right? Trace of A times B and trace of B times A are the same. And the reason that I'm writing it there are two reasons. First of all, you don't need to remember exactly the order and which matrix you need to put a transpose on. Right? This is nice. And second is because I actually want to choose the trace of B transpose times A as the standard notation. Again, they don't really matter, but this is what is usually used. And this is very similar to what we had in the standard in the product. Like the second variable appears first together with the transpose. And again, I will show you soon why this is better. Okay, so now we have a well-defined function which is linear and symmetric, and we only need to show that it is non-negative. And the way that you prove that it is non-negative is by actually writing down what it means. So if you open up what is the trace of B transpose times A, you get that it is just the sum of Aij, Bij, where Ij runs over all the coordinates. Or in other words, this is just a standard inner product on a vector, but we rearrange these vectors inside matrices. So if the standard inner product is actually an inner product, then this new standard inner product on matrices is also an inner product. So again, this is the same, just in a different arrangement. Okay, so this was three more or less standard inner products. I want to talk about another example, a bit less standard, and we're going to talk about real polynomials of degree at most d. So I'm going to define the product of f and g as the sum from k runs from 0 to d of fk times gk. And again, to show that this is a well-defined function, this is easy, and linearity is easy, and symmetricness is easy. Again, all of these follow because the product of fk and gk is distributive and symmetric. And by the way, in most cases, when we define new inner products, these three conditions will be easier. These are the more algebraic conditions. And the non-negative part, the geometric part, will be the more interesting one. So let's show that this is indeed non-negative. So basically, we need to multiply a vector by itself, a polynomial by itself, which is the sum of fk squared. So this is always non-negative. And what we want to show is that if this is 0, this is true if and only if the vector itself, if and only if the polynomial itself is 0. Now, if we take the sum of squares of real numbers and it is 0, then this means that each one of these numbers must be 0, or in other words, the polynomial has d plus 1 roots at 0, 1 until d. And now we suddenly can use a very interesting property of polynomials. Right? So if we have a polynomial of degree at most d and it has at least d plus 1 roots, then it must be the 0 polynomial. Right? So this means that a non-negative condition of the inner product space holds. Now, I want you to pay attention to what happens here. On the one hand, we had this interesting property about polynomials. Right? A degree at most d polynomial with d plus 1 roots is the 0 polynomial. On the other hand, we have this non-negative condition of inner products, and they're basically the same. And now suddenly it's really weird because the non-negative part came from the fact that we have the intuition about the plane. This is going to be a length of some vector, and somehow it is connected to this interesting property about polynomials. And I think that this is really one of the most interesting part about inner product, that we can codify using this simple definition lots of interesting properties about any sort of vector spaces. Okay, so these were 4 examples. I want to talk about another 2 examples, but this time in infinite dimension. Now, in general, this course is about finite dimension vector spaces. However, a lot of what we're going to talk about is still true in infinite dimension, but not everything. So let's see a little bit what happens there. So we can talk about standard inner product on R infinity, or in other words, about sequences over the real numbers. And we can define it similarly as before as the sum of ai bi, where I runs from 1 to infinity. So the fact that it is non-negative, symmetric, and linear in the first variable, again, very easy, very similar to what we saw before. The only problem is that this is not a well-defined function, right? Because in general, you sum up infinitely many numbers, it doesn't have to converge. So the way we fix it once we go to infinite dimension is instead of working over all sequences, we only work with, in a sense, finite sequences. But we define this finiteness using this condition that the sum of ai squared from 1 to infinity is finite. And you can show, and we might show something similar in the future, that if you have two such sequences and you define this multiplication, then this is always well defined. Okay. So once you reduce yourself to this type of sequences, which are really important, then suddenly you have an inner product structure on this infinite vector space. Okay, so this is one example. And the second example is whenever you have infinite sum, you also have integrals. So if you want to talk about continuous functions on 0, 1, and you define the product as the integral between 0 and 1 of fx times gx, then you get an inner product. So now this is a well-defined. Again, this is because you can always integrate a continuous function. The linearity and symmetricness are again easy. This is because the product is linear or distributive and the product is symmetric, and the integral function is linear. And again, the most interesting part is the non-negative. So we want to show that if the product of f by itself is, if the integral of 0 to 1 of fx squared is 0, this is if and only if f by itself is 0. Now, of course, if we integrate 0, we get 0. But if we integrate fx squared and get 0, why does it mean that f is 0? Right? Again, there is something interesting here, which can be transformed to the fact that the inner product is non-negative. And now this is again an interesting property of the continuous functions and integration. If you integrate a continuous non-negative function and you get 0, this is if and only if the function itself is 0. Okay, so again, we see something very interesting codified inside the inner product. Okay, so these are the 6 examples already to show that this interesting inner product definition has some merit to it. I want to return to the finite dimensional case, and up until now we talked about real numbers, and you can also define inner product over complex numbers. Now, if you are not familiar with the complex numbers, these are fine. You can still talk about only real numbers, and once you know about complex numbers, you should return here. But in general, you should learn about complex numbers, because while it takes a little bit to get comfortable using them, once you do, they are much, much simpler than real numbers. Right? There are all sorts of theorems about problems which appear over the real numbers, which disappear completely over the complex numbers. Right? So this is a little bit of motivation why you should know about it. Okay, so we talk about vector spaces over the complex numbers. And if you want to define an inner product, then this is a function. Again, it takes two vectors and returns a complex number. The non-negativity stays the same, but I want to emphasize this means that a v times v is now a real number and a non-negative one. Right? Because in general, the product is a complex number. It must be real number and non-negative. And the main difference is in the symmetric condition. This is no longer symmetric. It is called Hermitian. And you can still switch around the order of v and w, but you need to add the complex conjugation. Okay, so once you switch, you add complex conjugation. And linearity in the first variable stays the same. Okay, so let's see in the examples how you change them to be over the complex numbers. So first, instead of Rn and Rn to the m, we take the complex numbers, so Cn, or the matrices over C, or the complex polynomials of the grid D. And the way that we change the actual definition of the inner product is that we add complex conjugation, and always on the second variable. And I will let you check that these products actually satisfy the conditions of the inner product. And in the next video, we will see why we need to add the complex conjugation on the second variable and not on the first one. Okay, but you should check that actually they satisfy the inner product. So one last thing before I finish, I want to give you one last notation. So if you have a matrix and you see M star, this is just to take the matrix M, you apply the transpose and you apply the complex conjugation. Right? This is just what we see in the first example and in the third one. And this is why before I told you that we usually take W to be first or B to be first, because then we can put both the transpose and the complex conjugation on the same variable instead of splitting them to two parts. Okay, so this is an interesting notation. So if you read anywhere else about matrices, about inner products, and you see this notation, this is what it means. Okay, so today we saw what are inner products. And again, we started with the very simple intuition we have from the standard Euclidean geometry. And little by little, we try to extend it and generalize it. And again, I think that the most important part that we saw today is that this non-negativeness, one of the conditions, can codify all sorts of interesting ideas and all sorts of interesting properties about vector spaces. Okay, so this is enough for today. Next time we talk about properties of inner product spaces and more try to extend our intuition to these inner product spaces.